Okay, let's unpack this.
Let's do it.
So if I were to ask you, you know, how much of the Earth is made of dark matter?
Right.
Your first instinct, and I think this is true for most people, would be to, well, to correct me, right? To say the question itself is wrong.
To say that's not even the right
Yeah.
frame. Exactly. We're taught that dark matter is this huge galactic scale problem, a cosmological enigma.
Yeah, exactly. It's something we measure in halos and clusters, way, way out there. The idea that the local density is anything but negligible is, well, it's not the consensus.
And that consensus, while it's been mathematically convenient for a lot of cosmological models, has always rested on this one huge assumption.
Which is?
That our traditional ways of measuring mass, our gravitational methods, were robust and accurate at every scale.
Okay.
But what's fascinating here is that the whole idea of a purely diffuse dark matter halo, one that only weakly touches local systems like ours, is being seriously challenged now.
Challenged by what?
By new, and this is the key, non-gravitational data sources. And the implication is, well, it's that the density of dark matter around, and actually within, our own planet has been systematically and maybe grossly underestimated.
And that leads us right to the jaw-dropping statistic that is really the anchor for this whole deep dive.
Mm-hmm.
A recent analysis from 2023 that didn't use classic gravity.
Mm-hmm.
It used the physics of neutrino oscillation from these massive detectors, IceCube, Super-K.
A completely different way of seeing the Earth.
And it suggests that a staggering amount of this invisible stuff could be trapped right here. I mean, we are talking about the distinct possibility that up to 20% of the entire Earth's mass is composed of dark matter.
20%. Just let that sink in for a moment.
Yeah.
It's not a rounding error. It's a parallel component of our planet, a massive hidden structure.
Hidden in plain sight.
And this profound reevaluation of what our planet is actually made of, it forms the basis of the theoretical framework we're exploring today.
A framework laid out by J. Alfred, who's an independent researcher specializing in plasma and what he calls dark astrobiology.
Right. And it's important to note, Alfred has been questioning these low local density estimates since, 2007? Long before this new neutrino data came out, he was already on this track.
So his core thesis, which we're going to call the dark Earth model for this discussion, is that our ordinary matter, planet, the rocks, the oceans, us, is interpenetrated by a series of self-interacting dark plasma bodies.
He calls them dark plasmaspheres or dark Earths.
And these aren't just like invisible clouds of particles. Alfred argues they're highly structured systems.
Oh, incredibly structured. Complete with their own fields, differential rotation, and, this is the most surprising part, their own parallel biospheres.
Capable of hosting immense populations of life.
Which is where this deep dive is going. Our mission here is to explore the formation, the structure, the potential habitability of these theorized dark Earths.
And we're going to get into the science that suggests dark matter is way denser around here than we thought.
We want to take you deep into the physics that would allow for these stable, massive plasma bodies to even form, and then, explore the profound biological implications.
So you can understand a model where physics and biology just intersect in a parallel reality that's only accessible through these subtle, non-standard interactions.
Let's start with that scientific shift in perspective. The old number, the conventional wisdom for dark matter density around Earth, was about 0.3 GeV per cubic centimeter.
Which translates to what, roughly?
Roughly 1 particle per cubic centimeter, so very, very diffuse.
But Alfred, back in the mid-2000s, was already arguing that this number had to be. It had to be much, much higher to explain certain anomalies he was seeing.
And that intuition, that initial questioning, it found support pretty quickly from outside his own work. In 2008, physicists Zhu and Siegel published a paper that was really influential.
What did they find?
They did calculations that estimated the dark matter density near our sun to be approximately 16,000 times higher than that standard galactic halo density.
16,000 times. That's not a small correction. That's a different reality. How on earth did they arrive at that number?
Well, they modeled the gravitational capture of WIMPs weakly interacting massive particles over the entire 4.5 billion year lifetime of the solar system.
So they were looking at how much dark matter would have just sort of fallen into our solar system's gravity well over time.
Exactly. And their conclusion was that a huge amount, something like 7.69 times 10 to the 19 kilograms of dark matter, an immense mass, had become gravitationally bound and just accumulated inside the orbit of Neptune.
So this isn't some diffuse background we're flying through. This is a dense, localized concentration that's been building up for eons.
That's the key. And this idea of an elevated local density wasn't just theoretical. It started to correlate really strongly with real-world observations, things that standard Newtonian gravity couldn't quite explain.
The spacecraft anomaly.
Spacecraft anomalies. Stephen Adler, who was at the Institute for Advanced Study in Princeton at the time, he explored this back in 2009. He pointed out these unexplained acceleration anomalies seen in all these different space probes, Pioneer, Galileo, a few others, as they did their flybys of Earth.
They weren't moving exactly as predicted.
Not quite. They were behaving as if there was an extra gravitational pull, as if there was significantly more mass right here, locally, than we were accounting for. Adler concluded that to explain these persistent little deviations, you needed dark matter densities that were many orders of magnitude greater than the accepted galactic halo number.
So it points to a localized phenomenon.
Yeah.
It's not just the whole solar system moving through a cosmic fog. It's something centered right here.
Precisely. And Adler, echoing some of Alfred's earlier concerns, he suggested an accumulation cascade.
A feedback loop.
A feedback loop. Once you get a critical mass of dark matter gravitationally captured by a planet or star, it increases that body's gravitational cross-section, which means
it's better at capturing more dark matter.
At an accelerating rate. But, and this is a huge but, for this kind of rapid accumulation to happen, the model needs a key piece of non-standard physics.
Which is?
Matter-antimatter asymmetry in the dark sector.
Meaning?
Meaning there has to be very, very little dark antimatter compared to dark matter. Because if the amounts were equal, the dark matter particles would just annihilate each other on collision.
And you'd never get any large-scale accumulation.
You'd get a fizzle, not a planet. So Alfred's dark Earth model explicitly relies on this crucial assumption. The dark matter is asymmetric and self-interacting. It can bump into itself and build things, not just destroy itself.
And around this time, the idea of large-scale dark matter structures, beyond just a simple sphere around the galaxy, was also gaining traction, right?
It was. In 2012, a team at the University of Zurich was measuring mass distribution in the Milky Way, and they found compelling evidence suggesting that, yeah, dark matter might be far more abundant locally than we thought.
Which ties into the dark disk idea.
The Randall-Rees dark disk model. The idea that dark matter isn't just a big spherical cloud, but that some of it has flattened into a dense disk structure within the galaxy.
A disk that we, the solar system, are currently flying through.
Exactly. And Alfred integrates this into his model. He proposes that the dark matter in this disk, because it's so dense and so close to ordinary matter, would naturally be the type his model needs. Self-interacting, with a weak, dark electric charge. It connects the microphysics of accumulation to the macrostructure of our galaxy.
And maybe the most direct piece of evidence for all this uncounted mass came from something we use every single day.
Our navigational satellites.
Yeah.
Professor Ben Harris in 2014 used super precise acceleration data from GPS, GLONASS, Galileo, the whole suite.
Okay.
By meticulously tracking the orbital dynamics of these satellites, which are incredibly sensitive to tiny local gravitational changes, he came to a definitive conclusion.
The Earth has more mass than we thought.
Significantly more mass than the official standards set by the International Astronomical Union. And since ordinary matter couldn't account for these weird accelerations, the inference was clear. There's a massive uncounted component, a substantial halo of it, right around our planet stretching far above the atmosphere. It was gravitational confirmation of the kind of accumulation Alfred had been hypothesizing.
So we've established that a huge amount of dark matter has been captured. But it's not a one-time event, right? This material has to be flowing in from somewhere continuously.
The sources are manifold and constant. The dark Earths are always being fed, so to speak. First, you have what you could call dark matter clouds, streams, and rain that are always passing through our part of space.
Right.
A physicist named Jurg Diamond, he did these computations that showed these small flattened spheres or cigars of dark matter, huge structures, maybe 4,000 AU in diameter.
Far bigger than our whole solar system.
Way bigger. And these things pass through the Earth approximately every 10,000 years.
10,000 years sounds kind of rare.
It does, but the duration of the encounter is what matters. Diamond suggested each passage would last for about 50 years.
50 years of passing through a denser cloud of dark matter.
Right. And while the density in these clouds isn't high enough to, knock us out of orbit or anything catastrophic, the sheer frequency of these encounters over the solar system's entire history, it represents a consistent supply line. It's constantly refreshing the local dark matter density.
Now, there's just the sheer volume we've passed through by just moving through the galaxy.
It's an astonishing number. You and Siegel calculated this. Over its 4.5 billion-year journey around the galactic center, our solar system has waded through an estimated 203 solar masses of dark matter.
203 suns worth.
203 suns worth of exposure. Think about what that means. Every single kilogram of ordinary matter on Earth, your body, the chair you're sitting in, has been consistently exposed to and has encountered thousands of dark matter particles every single day for billions of years.
So the capture process isn't just possible, it's utterly inevitable.
It has to happen, and we might be passing through a particularly rich stream right now.
Because the Milky Way is a cannibal.
It is. Our galaxy is currently in the process of tearing apart the Sagittarius dwarf galaxy, stripping away its dark matter halo.
Okay.
And researchers propose that this process creates a detectable, focused stream, a dark matter highway that's flowing directly through our solar system right now, significantly boosting the local density.
So beyond these external sources, the big gravitational player in our neighborhood, the sun, it has to be a massive dark matter sink. It must be creating what Alfred calls the invisible sun.
Absolutely. The sun's gravitational cross-section is so enormous, it's just constantly capturing a huge volume of any dark matter particles that pass by.
Has anyone calculated the effects of this?
Oh, yes. The physicist Iorio did back in 2010. He calculated the cumulative effects of this solar accretion. His estimate was that if the current rate of capture continues for the next 4.5 billion years,
The remaining lifespan of the sun.
the Earth's orbit will shrink to about half its current distance from the sun.
Wow. Just from the invisible increase in the sun's mass.
Solely from that. Which is a powerful calculation because it implies the sun is already significantly heavier than its ordinary matter suggests it should be.
And this buildup isn't just some passive side effect. You're saying it could actually solve some of the most persistent, nagging mysteries in solar physics?
It could, specifically the solar composition problem and the solar abundance problem.
Okay, how does invisible matter fix problems with visible matter?
Well, physicists like Sarkar and Franzen estimated that the visible sun probably contains between 2 and 5% of its mass in the form of this captured dark matter.
Right.
And because Alfred's model assumes this dark matter is light and self-interacting, it builds up densely in the sun's core. And here's the key. While it interacts weakly with our kind of matter, it interacts strongly with itself.
Creating a unique thermal mechanism.
Exactly. This dark matter acts like an internal heat conveyor belt. The dark particles absorb heat in the ultra-hot core, they move outward, transport that heat toward the sun's surface, and then cycle back to the core.
A completely parallel system for heat transport.
Yes, and this mechanism, which was also proposed by Stephen West, it effectively reduces the core temperature and just changes the whole thermal profile of the star.
And that resolves the abundance discrepancies.
Yes. By lowering the core temperature, it brings the standard solar model's predictions for how elements should be distributed, especially heavy elements, into perfect alignment with what we actually observe.
That's a pretty compelling piece of evidence.
It's one of the strongest arguments for self-interacting dark matter inside stars. But we have to stress it again. This entire mechanism, the accumulation, the heat transfer, solving the solar problems, it all hinges on that key assumption.
Asymmetric, self-interacting dark matter.
It has to be able to build up and stick around without annihilating.
Okay, so if the sun is this massive reservoir of dark matter, it must also be ejecting particles. It's a star.
That's the dark solar wind. If the sun has this huge dynamic reservoir of dark matter inside it, it has to be constantly ejecting its later component.
What would that be made of?
Dark protons, dark electrons, dark photons, propelled by dark radiation, shaped by dark magnetic fields. This unseen flux would just be constantly flooding the Earth with trillions of dark matter particles every second.
Actively fueling the growth and maintenance of these dark Earths.
Ensuring continuous accretion, it's the final piece of the local supply chain.
Here's where it gets really interesting. We have to tackle the central problem that let this, potential 20% mass component be missed for centuries. If it's so massive, so gravitationally powerful, how did scientists just not notice it?
The answer is something Alfred calls mass conflation. It's a really simple but profound idea.
Okay.
For centuries, starting with Newton, the way we calculated the Earth's mass was by measuring the gravitational acceleration on things near it. The moon, an apple, whatever.
Right. GMHWR2.
Exactly. But that process operated under a critical and completely untested assumption that the m, the mass, was only due to ordinary matter, the rock, the iron, the liquid core.
So the measurement itself was the problem. We're measuring total gravity, but just assuming its source was singular.
Precisely. If there is localized dark matter, which accumulated through that cascade process we talked about, and it's exerting its own gravitational pull, that force was just misattributed. It was conflated with the mass of the ordinary stuff.
Can you give us an analogy for that?
Sure. Imagine you have a scale that measures total weight, but you can only see what's on the left side of the scale. That's ordinary matter.
Okay.
If there's an invisible, perfectly balanced weight on the right side of the scale, that's dark matter, the scale reads the combined total. If you calculate the density based only on the visible objects, you'll conclude those visible objects are way denser and heavier than they actually are.
The gravity from the dark matter just got lumped into the mass density we assigned to the ordinary matter.
It was hiding in plain sight in our own equations. And this is why, as Alfred points out, the fact that the solar system obeys Newton's laws doesn't rule out the dark Earth at all.
Explain that.
He has this simple thought experiment. If the Earth and the Sun were made entirely of dark matter, but had the same masses and orbital momenta we currently ascribe to them.
They still orbit each other perfectly, according to Newton's laws.
Perfectly. Gravity measurements alone can't distinguish between the two types of mass if they're distributed in roughly the same way, which means our traditional methods, gravimetric measurements, even seismic wave analysis, are all inherently flawed.
Because the seismic data relies on density figures that were derived from those same gravitational assumptions in the first place.
It's a circular argument that perpetuates the conflation.
So to break that circle, we needed a measurement method that was completely independent of gravity. Which brings us back to the breakthrough, neutrino tomography.
This method is just brilliant because neutrinos are almost perfect probes for this.
Why?
They're immune to the strong nuclear force and the electromagnetic force, so they don't care about the charge of ordinary atoms. They only interact through the weak nuclear force and gravity.
And the weak force interaction depends only on the density of particles.
Both ordinary and dark. It gives you a mass density reading that is completely independent of how that matter behaves gravitationally. It's a true mass census.
So how does the tomography actually work with a detector like IceCube?
So researchers measure atmospheric neutrinos, which are constantly raining down on the planet, and they watch how these neutrinos oscillate between their three different flavors, electron, muon, and tau, as they travel through the Earth.
And the rate of that oscillation changes depending on what they pass through.
Exactly. The rate is affected by the total matter density they encounter. So by mapping these oscillation patterns as they go through the core, the mantle, the crust, scientists can get a sense of the total mass density, the sum of ordinary and dark matter, without any gravitational assumptions at all.
And what did the hard numbers from that 2023 analysis tell us about this hidden component?
They gave us very significant upper and lower bounds. The IceCube data ruled out the possibility that more than 24% of the Earth's total mass could be dark matter.
Okay, so there's a ceiling.
There's a ceiling. And a similar ceiling for the core at 32%. The Super-K experiment in Japan gave similar constraints, ruling out more than 21% for the whole planet.
The implication there is pretty clear. We have an independent, non-gravitational method setting an upper limit that is, well, it's very high.
It's incredibly high. And when you combine these constraints with the observational anomalies we talked about, from Adler's spacecraft, from Harris's GPS data, the conclusion tightens up significantly.
And the number is?
It's plausible that 20% of the entire planet's mass and about 30% of the core's mass may be dark matter.
Which aligns perfectly with Alfred's argument about where this dark matter should accumulate.
Right. It should be most concentrated where the overall gravitational potential is highest.
But wait, why is the density highest in the core? If the dark matter is accreting from the outside, shouldn't it be, like, coating the outside of the planet?
That's a crucial question, and it gets to the relationship between the two components. Alfred argues that while dark matter dictates structure in the huge galactic scale, on smaller scales, like planets and stars,
The ordinary matter calls the shots.
the immense gravitational force from the much, much denser ordinary matter dominates. It acts as this massive gravity well that tells the self-interacting dark matter where to go and where to compactify.
So the ordinary Earth is like a physical template or scaffolding.
A gravitational scaffolding,
Yeah.
yes. Since the ordinary matter density and the gravitational potential are at their absolute maximum in the core, that's where the heavy, self-interacting dark matter particles will sink and accumulate.
You get a particle-for-particle correlation.
You do. And this concentration is likely mediated by that conjectured but necessary fifth force, an attractive force between dark and ordinary matter, which allows them to couple gravitationally in a much tighter way than standard models would predict.
If we connect this to the bigger picture, then, we have to understand what state this 20% dark matter component is in. Alfred is very clear. It's not a solid, not a gas. It's a self-interacting dark plasma.
And that idea is rooted in the hypothesis that at least some dark matter has a weak dark electric charge.
How weak are we talking?
Yeah.
And why is that weakness so critical for the model?
Well, theoretical physicists like Avi Loeb have suggested this charge could be as small as 1/1,000,000th of an electron's charge, so incredibly weak.
Okay.
And that extreme weakness is fundamental. In ordinary plasma, you have a strong electromagnetic force that dictates rapid interaction, rapid neutralization. But Alfred argues that the dark Earth material exists as a plasma because of three factors that suppress that neutralization.
Factor one is the weak charge itself.
Right. The weak dark electric charge is just not strong enough to bind dark protons and dark electrons together quickly. The binding energy is so low that the particles just stay ionized. They stay separate, which dramatically slows down the rate of recombination into stable neutral dark atoms.
Okay. And factor two is about the weird composition of the dark universe.
This is where it completely flips our normal expectations. In our universe, charged particles, protons, electrons vastly outnumber neutral particles by about 14 to 1.
Right.
In the hypothesized dark sectors, Alfred argues the reverse is true. There are roughly 5 times more neutral dark matter particles than charged ones.
And what do all those neutral particles do?
They act as a superb buffer, an insulator. They physically get in the way, insulating the charged particles from each other and suppressing recombination even further.
And the third factor is just about the density of the material itself.
Even though 20% of Earth's mass is immense, the particle density of dark matter is still many, many orders of magnitude less than ordinary matter. This means the mean free path, the average distance a particle travels before it hits something else, is extremely long.
So it's just a less crowded environment?
Much less crowded. And that combination weak charge, abundant neutrals, low density, means that the non-atomic, self-interacting dark plasma state isn't just possible, it's the default. It's the inevitable low-energy state for this kind of material.
Alfred also calls this a complex dark plasma. What makes it complex or dusty?
So in lab physics, a complex or dusty plasma is one that has large non-standard particles mixed in, like literal dust grains. These grains acquire a huge negative charge and start to generate really intricate plasma structures and waves.
And Alfred thinks the dark Earth plasma is like that.
He theorizes it's an analog. It might contain large non-standard dark matter particles. He speculates about things like supersymmetric cue balls that act like these highly charged dust grains. Their presence would polarize the surrounding plasma and generate the kind of intricate, highly structured features his model requires. It's not just a simple ball of gas.
Let's talk about how this immense plasma body, this dark Earth, actually came into being. Alfred suggests a top-down genesis, which is the complete opposite of how our regular Earth formed.
And that contrast is absolutely essential. Our ordinary Earth formed bottom-up. Countless smaller pieces planetesimals accreted over time, bound primarily by the strong electromagnetic force.
Right.
Dark Earths, he argues, formed top-down. They started as a much larger, more diffuse dark matter halo that gradually underwent gravitational contraction and cooling. The ordinary matter Earth then formed inside the gravitational well of the largest and lowest energy dark Earth that had already stabilized.
And based on plasma physics, these dark Earths would be huge, way bigger than our planet.
They are massive plasmaspheres. Alfred's calculation suggests that the smallest one, the lowest energy one that's coupled to our planet, has a theorized radius of 70,000 kilometers.
70,000. And that number, that's the Adler line estimate, right? It links the structure back to that anomalous space probe data.
Exactly. It's all connected.
Let's try to visualize that scale, 70,000 kilometers.
If you compare its volume to the ordinary Earth's volume, this one dark Earth could fit over 1,000 ordinary matter Earths inside it. It's this low-density, massive structure. It's a unique astrophysical object, kind of like a brown dwarf, but without enough mass for fusion. And it's co-rotating with our Earth,
Right.
with the two structures just mostly passing right through each other.
Our solid Earth is pretty static, but a giant ball of plasma has to be incredibly dynamic.
It's in constant flux. Alfred describes it as constantly size-shifting and shape-shifting, like a dancing candle flame.
What's causing that flux?
It's being buffered by external things like the dark solar wind we talked about and internal gravitational tides from the ordinary Earth and Moon. And because it's a rotating ball of plasma, it experiences differential rotation.
It spins faster at its equator than at its poles.
Right, which generates a powerful Coriolis force. And that force, in turn, creates these vast, coherent plasma vortexes, the dark matter equivalent of Jupiter's Great Red Spot.
And if you were an observer in the dark sector, you could actually see this thing. It wouldn't be black. It would be shimmering.
Precisely. Plasma spontaneously emits radiation. In this case, it would be dark photons, or what Alfred calls diffuse dark light. The visibility of the dark Earth to an external observer would flicker based on the relationship between its own internal plasma frequency and the ambient dark light coming from the dark sun.
So if the internal plasma density changes,
The frequency changes. If the internal plasma frequency is high relative to the ambient light, the dark Earth could appear to shine like a metal ball. If the frequency is lower, it becomes transparent and just vanishes.
and since the density is always changing from the buffeting of the solar wind and gravity.
It results in a constantly shimmering or scintillating appearance, an invisible structure that sometimes phases into a visible state, at least in its own sector.
Okay, let's move inside this immense plasmasphere.
Where?
How is the mass actually distributed? We know the lambda cold dark matter model predicts these central cusps of high density in galaxies, but that doesn't really hold up at planetary scales.
No, it doesn't. And at these smaller scales, as we noted, the dark matter density seems to follow the distribution of the ordinary matter.
Right.
That's the key observation, and it's supported by multiple studies. Physicists like Manoj Kaplinghat showed that self-interacting dark matter density profiles correlate very strongly with ordinary matter density in galaxies.
High brightness galaxies have high dark matter density, low brightness galaxies have hollow cores.
Exactly, and that strong correlation suggests an attractive force is mediating the interaction. It's that conjectured fifth force again. It's what allows them to talk to each other gravitationally.
So on planetary scales, the sheer density of our ordinary matter, Earth, just dictates the whole structure.
It dominates the dynamics. It tells the self-interacting dark matter where to settle, where to compactify, which is why the highest concentration of dark matter ends up below our crust, right where our ordinary matter is densest. It matches the neutrino tomography findings perfectly.
Now we have to layer in the electrodynamics, the charge stratification that creates the E plus and E regions. This is the planetary capacitor.
Charge separation happens in all plasma, but it's uniquely stable and long-lived in the dark Earths.
Why?
Because of the low particle density, the weak dark electric charge, and crucially, the prevalence of neutral particles. Those neutrals, which outnumber the charged particles more than 5 to 1, act as an incredibly effective and sustained dielectric medium, an insulator.
And the mechanism driving this vast separation is the Panacuk-Rosslin field.
Correct. It's a mechanism based on gravitational stratification. It sorts particles by mass. Think of it like a centrifuge or a big jar of muddy water. Gravity pulls everything down.
But the heavy stuff sinks faster and farther.
Right. And since dark protons are almost 2,000 times more massive than dark electrons, the heavy particles sink rapidly and the light particles are left to hover. This creates a massive polarity across huge distances.
So where do the heavy positive particles, the dark protons, settle?
They form the E+ region. The heavy, positively charged, and relatively cold dark protons sink all the way to the Earth's core. They create this dense, non-neutral plasma region deep below the ordinary matter crust. That's where the highest mass density of the dark matter component is.
And the light, negative electrons.
They form the E region. The light, negatively charged, relatively warm and energetic dark electrons, they hover in this huge spherical shell surrounding the planet. Their peak concentration is theorized to be right around that Adler line at about 70,000 kilometers from the center. the edge of the plasmasphere.
This configuration is just a phenomenal electrical storage device.
It's the ultimate planetary capacitor. The E plus core is the positive electrode, the E shell is the negative electrode, and that immense volume of neutral dark matter particles in between acts as a massive dielectric insulator.
Which prevents the rapid recombination you'd see in normal plasma.
And allows the charge separation, which is absolutely crucial for any kind of biological evolution, to be sustained for billions of years.
So if we were to chart the density of charge, moving out from the center of the Earth, we'd see a very distinct wave pattern.
A highly stratified charge density wave. You'd move from a high positive charge in the E plus core
Out to a high concentration of neutrals, right around our ordinary matter crust and mantle, the main buffer zone.
Then you'd hit the peak negative charge in the E halo at that 70,000 kilometer Adler line.
And then back to a high concentration of neutrals in the collisionless dark plasma that stretches out into Earth-Moon space.
It's this nested shell structure. That is the fundamental topography of the dark Earth.
This implies that the Moon, which is obviously gravitationally coupled to us, must also be capturing dark matter and have its own halos.
Absolutely. The Moon is a gravitational sink, too. It accumulates dark matter, so it has to possess its own dark halos, or dark moons, with the same analogous M plus positive core and M negative shell regions. These two systems are constantly interacting.
And when the Earth and Moon are closest, there's a chance for a transient connection.
That's right. When the Moon reaches perigee, its closest approach, the mutual gravitational and electrodynamic attractions between the dark Earth and the dark Moon intensify.
Okay.
Alfred suggests this could allow a tenuous dark bridge to momentarily form, connecting the lowest energy dark Earth to the lowest energy dark Moon.
A bridge that could facilitate the exchange of dark plasma material.
And perhaps even dark life forms between the two celestial bodies.
So we've built this massive, structured, stable, dark plasma environment. Now we get to the most provocative part of Alfred's theory. The idea of a robust, parallel dark biosphere. What is it about this dark plasma that makes it uniquely suitable for life?
The single most crucial factor is the weak, dark electric charge.
Okay.
In ordinary high-energy plasma, the strong electric force drives these massive plasma instabilities, destructive turbulence, filamentation, kink modes. These things would immediately shred any delicate biological organization.
Life needs calm, and plasma is typically chaos.
Exactly. But the weaker charge in the dark sector dramatically suppresses those instabilities. It forces the plasma into a more stable laminar behavior. Instead of the wild turbulence you see in ordinary plasma, the particles might settle into these vast crystalline grids and concentric shells. It's just a fundamentally calmer, more ordered environment, which is conducive to long-term biological evolution.
And the stability of that charge separation is absolutely key for anything that resembles a cell.
It is the fundamental basis of biological organization. A cell membrane is, at its heart, a highly controlled charge separation boundary.
Right.
Ordinary plasma tends to neutralize itself very quickly, which would just erase that boundary. But the conditions in the dark Earth-weak charge, low density, abundant neutrals, allow this crucial charge separation to be sustained for billions of years. That provides the necessary physical substrate for complex dark plasma life forms to organize and evolve.
The idea of dark life has been a favorite speculation for a lot of physicists. I know Lisa Randall and Sean Carroll have both talked about dark chemistry, dark biology, maybe even dark civilizations, if dark matter interacts with itself.
They have, but Alfred proposed this much earlier, starting around 2005, and he based it on actual laboratory experiments using ordinary matter.
The Losnianu and Sandelovisciu experiments from 2003.
That's right. They were working with non-thermal, cold argon gas plasma and an electrical discharge. And they completely by accident created these structures that showed key attributes of primitive living organisms.
Let's talk about the structure they saw. What did it look like?
These things spontaneously organized into stable, hollow spheres, and crucially, they developed a double layer, an inner positive layer of ions, and an outer negative layer of electrons.
Which acts just like a cellular membrane.
Exactly like one. It confines the plasma inside and maintains that essential charge separation from the outside environment.
So they spontaneously form the basic architectural need for life. Boundary. What about dynamics? Do they do anything?
They exhibited these remarkable biological characteristics. First, mobility. At a certain voltage, they could actually detach from the electrode and exist in a free-floating state, moving around independently through the plasma.
And they could replicate.
They could. Under specific energy conditions, they would replicate by splitting, a process that is a direct analog to mitosis in biological cells.
The metabolic process was visually stunning, right?
It was. They showed these metabolic pulsations, a rhythmic wave-like expansion and contraction, which the researchers called a cyclic inhalation. It suggests a mechanism for processing energy and interacting with the plasma environment in a way that just perfectly mimics breathing and metabolism in living systems.
But the most striking thing was communication,
Right.
which Alfred connects to a kind of plasma telepathy.
Yes. The plasmaspheres showed they could communicate by emitting and receiving electromagnetic energy at specific resonant frequencies. When one sphere emitted energy, another sphere nearby would receive it and start to vibrate sympathetically. As Lozniano himself noted, if you didn't know the underlying physics of these electromagnetic waves, you would describe the process as telepathic.
A non-standard form of communication.
And it suggests that plasma systems inherently have the mechanism for complex information exchange built right in.
Given these stable conditions and the potential for organization, the scale of this parallel biosphere must be just staggering.
The scale is immense. As we said, the smallest dark Earth is over 1,000 times the volume of the ordinary Earth. Alfred conjectures that dark plasma lifeforms, or PLFs, are likely to outnumber ordinary carbon-based life by many thousandfold. Not just on Earth, but across the whole solar system where this dark plasma accumulates.
But where do they live inside this huge volume? It can't all be uniformly populated.
No, absolutely not. Alfred notes that most of the dark Earth is extremely low density and very sparsely populated. Life would be constrained to regions where the dark matter density is high enough, but not overwhelming, and where the mix of particles is ideal.
Specifically, where the density of neutral particles is highest to maintain that stability.
Which brings us to the most likely habitable zone, the overlap region. The highest concentration of neutral dark matter particles happens to coincide almost perfectly with the surface layers of our ordinary matter Earth.
So Alfred conjectures that the most robust population of these PLFs inhabits the CTS region.
The crust, troposphere, and stratosphere. A slice about 100 kilometers thick, extending roughly 50 kilometers above and 50 kilometers below the Earth's physical surface. This is the unique zone where the stable dark plasma meets the influence of the ordinary planet, creating optimal conditions.
And these life forms would just float in this expansive plasma ocean. They wouldn't need conventional locomotion.
Their movement would be fundamentally electrodynamic. They'd float and move using subtle shifts in localized electromagnetic fields. Slow movement would look like flying and swimming, while fast movement would be zipping through the plasma ocean at enormous speeds using electrodynamic propulsion.
And their boundaries, the double layers, act as physical confinement.
Right. If a PLF's internal energy is too low, it can't penetrate the strong electrical fences that surround other plasma cells or shells. This creates distinct and defined habitats within the larger plasma ocean.
The challenge, of course, is if they're right here, how do we prove it? This brings us to Alfred's proposed project, SITI, the Search for Interterrestrial Intelligence.
A project that would look for subtle clues in our ordinary matter sector, what he calls inbound manifestations, and also actively monitor the dark sector, which would be outbound.
The inbound manifestations are certainly the most captivating. The idea that all these different anecdotal phenomena might just be dark plasma life forms briefly appearing in our world.
Alfred suggests that the cold plasma envelopes generated by these PLFs, especially when they interact with intense geomagnetic fields or high-density ordinary matter, might briefly become visible to us.
And this could provide a scientific basis for a whole range of things, from modern UAPs and UFOs
to historical, culturally specific events like Marian apparitions, ghosts, and even jinns. The hypothesis is that these are all just different cultural interpretations of the same physical phenomenon, the interaction between a dark plasma envelope and our visible world.
Okay, let's focus on the two main scientific strategies for detection, starting with the dark ionization process and how it connects to sacred sites.
The core idea here is that the dark Earth isn't uniformly dense. It contains a grid of dark filamentary currents. These are regions of very high-density plasma within the larger plasmasphere.
Right.
And as these dense currents interpenetrate our ordinary Earth's crust and atmosphere, the collision rate between dark and ordinary matter particles goes up, which generates streams of weak, cold plasma. That's the dark ionization process.
And these dark currents are theorized to be the foundation for some long-standing metaphysical concepts.
Exactly. Alfred suggests these underlying dark filamentary currents map directly to what metaphysical literature calls Lilines.
Yeah.
And where these currents intersect and pinch, the dark matter density becomes extremely high, creating powerful vortexes that correlate spatially with locations that have traditionally been established as sacred sites all over the world.
Why would those spots be designated as sacred? What's the connection?
The dark ionization process happening in these vortexes generates a localized higher amount of cold plasma in our ordinary sector. And today, we know that cold plasma has remarkable healing properties.
It promotes wound healing, kills bacteria.
It influences the body's bioelectric field. Alfred suggests the presence of this healing, energizing cold plasma is the scientific reason these locations were deemed sacred by ancient cultures, which often led to healing pilgrimages.
So the detection method would be to monitor these specific sites.
Yes, the SITI project would involve continuously scanning and monitoring established sacred sites for slightly higher ionization levels, anomalous EM signatures, or increased infrared radiation. This would effectively map the underlying dark filamentary currents and test the hypothesis.
The second strategy involves kinetic mixing, where energy from the dark sector crosses over into ours, and that leads to that very specific phenomenon of the buzzing sound.
Right. The filamentary currents act as dark electromagnetic highways, where PLFs are likely to cluster. The metabolic processes of these life forms would generate exotic radiation in the dark photons, axions.
Okay.
When this dark radiation passes through high-intensity geomagnetic spots on Earth, kinetic mixing can cause a conversion into ordinary photons, manifesting as infrared radiation and, crucially, as microwaves.
How does that radiation become a sound that only one person can hear?
The microwaves produced by this process are capable of heating biological tissue, specifically the soft tissue in the head. This heating, even though it's slight, creates thermoelastic waves of acoustic pressure
Which travel through bone conduction to the inner ear.
and result in a perceived noise, a buzzing, a clicking, a high-pitched sound that is only perceived internally by the affected person. It's not audible to anyone else nearby. It provides a measurable, physics-based explanation for certain reported phenomena.
That specific localized acoustic effect is a pretty powerful candidate for a technosignature of an interterrestrial intelligence.
It is. And SITI could also try to eavesdrop for unnatural radio or optical signals in these high-intensity geomagnetic regions. If these cold plasma filaments are being used as information channels, like fiber optic cables.
Detecting unnatural patterns within them would be a measurable, physics-backed technosignature. It would suggest the dark currents are being actively used by technologically advanced dark life.
Finally, let's talk about the timing. Is this interaction between the dark Earth and our Earth constant, or is there a specific season when these manifestations might peak?
The interaction is modulated by orbital mechanics. As the Earth moves around the Sun, the density of dark matter particles raining down through us is not constant. It goes through an annual modulation, a seasonal variation.
The dark matter density peaks around June. That's when the Earth is moving in the same direction as the solar system is moving around the galactic center. It's like a cyclist riding directly into the cosmic wind and rain.
And this isn't just a theory. The Dama Libra experiment, a dark matter detector deep underground, it confirms this annual modulation with very high statistical confidence. They see a periodic increase in collision events centered right around the beginning of summer.
And that seasonal peak in dark matter rain creates a higher probability of interaction, and therefore a higher probability of observing the effects of dark ionization.
Which correlates strikingly with certain cultural phenomena.
It does. Alfred points to the Chinese Hungry Ghosts Festival, which is usually around August. This is traditionally when the gates of the underworld open and souls are believed to be freed to roam the Earth.
Meaning, the frequency of seeing these ordinary cold plasma envelopes of dark life forms would naturally be highest when the dark matter density is at its peak.
Precisely. This striking correlation suggests that these ancient beliefs might have a deeper scientific significance. The probability of visible interaction goes up during the period of maximum dark matter influx, which happens to line up with periods of traditional supernatural activity.
A meta-analysis of historical ghost sightings or UAP sightings correlated with the Dama Libra data could provide some pretty strong empirical support for this.
To synthesize this whole immense deep dive into J. Alfred's work, we really started by challenging a basic assumption about negligible local dark matter, and we ended by proposing a massive parallel civilization.
Yeah, we established that up to 20% of Earth's mass is likely dark matter, a figure that comes from independent neutrino tomography, which solves that problem of gravitational mass conflation.
And that this material forms dark plasmaspheres, these highly stable planetary capacitors with a positive core, the E plus N, and a negative halo. The E, whose stability is ensured by a weak charge and a huge abundance of neutral particles.
These dark Earths are huge. The smallest is over 1,000 times the volume of our planet, and they harbor life. The stability suppresses plasma instabilities. It sustains charge separation, and it allows dark plasma life forms to thrive in that vast, overlapping CTS region of our planet.
The crust-troposphere-stratosphere overlap zone.
So what does this all mean? The source material concludes that this vast, ancient life form might only be detectable through these rare, subtle, non-standard interactions, like that internal buzzing sound for microwave conversion or the anomalous ionization at sacred sites that maps the underlying dark grid.
Given the compelling evidence that up to 1/5 of our planet is made of this unique substance, the possibility is that the most widespread, ancient, and maybe the most technologically advanced life form on Earth isn't carbon-based at all.
But is instead hiding in plain sight, within the very fabric of our world, interpenetrating us completely.
So we invite you to consider what subtle, unexplainable anomalies that sound only you can hear, that unexpected feeling of serenity at a specific spot, or that fleeting shadow you can't quite place might you encounter in your daily life that could, in fact, be an interterrestrial signature.